Liquefied gas carriers are among the most specialized ships trading today. They have very specific cargo containment and cargo handling systems. This training video provides an introduction to these ships, their cargoes, and their safety systems. To understand these ships, it's necessary to know something about the liquefied gases that they carry. There are several types of these gases. First, liquefied natural gas, LNG. This is principally methane. Secondly, liquefied petroleum gas, LPG. This is usually propane or butane. Lastly, chemical gases, ammonia and vinyl chloride monomer, VCM, chlorine and others. This group also includes some hydrocarbon gases such as ethylene, propylene, butylenes and butadiene. Each of these gases has different properties and potential threats to personal safety. These are described in the materials data sheets that you'll find on board. The data sheet for the cargo being carried must be prominently displayed. These gases have different types of ship designed to carry them. One thing they all have in common is that under normal atmospheric temperatures and pressures, all these compounds are gases. Gases are liquefied for transportation because they occupy several hundred times less space as liquids. Knowledge of the physical behavior of gases will help you understand why the systems on board work the way that they do. The most important thing for their transportation and handling is how these gases behave at different temperatures and pressures. This is often shown on a graph called a vapor pressure diagram. The temperature in degrees Celsius is shown horizontally, with the pressure vertically. For convenience, this is generally expressed as the saturated vapor pressure, SVP, in a non-linear scale. The units used here, kilograms per square centimetre, are equivalent to bar or normal atmospheric pressure. Each gas has its own individual curve on this graph. Its SVP is the pressure exerted by the boiling liquid vapor of the gas within a closed container at a given temperature. Effectively, the conditions when the gas becomes a liquid and the liquid can become a gas. This is the curve for butane. So, under conditions to the left of the curve, butane is a liquid, and to the right it is a gas. We can see that at 0 degrees Celsius at 1 bar, butane is a gas. 1 bar absolute is the equivalent of 0 gauge pressure. If we go up the curve, we can see that a pressure of 3 bar is enough to keep it a liquid at temperatures of up to 30 degrees Celsius. This is the kind of pressure that exists in a disposable cigarette lighter, enough to keep the butane as a liquid. If the pressure is released, gas escapes. In doing this, you have effectively moved the conditions of the butane into the gas area of the graph. These are the curves for other common liquefied cargoes: methane, ethylene, propane, propylene, ammonia and vinyl chloride. If we look at the curve for propane, we see that in theory it could be carried at atmospheric pressure if it is kept below -42 degrees Celsius. Or it could be carried at temperatures up to +40 degrees Celsius if it is kept at a pressure of 10 bar or more. Looking at the curve for methane, natural gas, we see that it will always need to be refrigerated as even at a 40 bar pressure, it must be kept below -80 degrees Celsius to remain a liquid. Sometimes mixtures of gases are carried. The SVP of the mixture will depend on the proportions of the two gases in it. In a simple mixture of, for example, ethane and methane, the curve will lie somewhere between those of the separate gases. As their basic structure shows, gas carriers were developed from oil tankers. But there are many differences. For example, in oil tankers, the hull often forms part of the cargo tanks. But in gas tankers, the cargo tanks are always separate structures inside the hull. Another important difference is that oil tankers always have inert gas in the vapor space above the cargo. In gas carriers, there is no inert gas or air at the top of the tank, only cargo vapor. The design and building of gas carriers must conform to the gas codes of the International Maritime Organization, the IMO. These codes go into great detail about all aspects of the design of the ship and their cargo tanks. The code specifies the maximum pressure and equipment required for different cargoes.
A secondary barrier may be required to protect the hull from any leakage from the cargo tanks. This depends on the type of containment selected and the temperature of the cargo to be carried. All tanks are tested before they're used to carry cargo. The tanks have to withstand the large thermal stresses provoked by cooling down on loading after dry dock and warming up after gas freeing. But during cargo and ballast voyages, the tanks are usually kept at low temperature, often by retaining a heel, a small part of the cargo, on board. Some ships have specialized equipment to re-liquefy the cargo. Many are equipped with inert gas or nitrogen systems to inert the hold spaces around the tanks. Liquefied gas carriers use a variety of cargo containment systems. The choice of system is determined by the temperature and pressure required by the cargo and the cost of suitable engineering to contain it. The reactivity of certain chemical gases will restrict the construction materials that can be used. The more you understand about your own ship, the better. Time spent studying the regulations and how your ship conforms to them, as well as how its special equipment is operated, is time well spent. In this video, we cannot deal with every liquefied gas carrier, only the most common types, starting with fully pressurized ships. Fully pressurized ships carry their cargo under pressure, but at ambient temperature. They're generally smaller than other gas carriers. They usually have cylindrical cargo tanks that are able to withstand pressures up to 18 bar, although on some ships the maximum is only 10 bar. These are called Type C tanks after their designation in the IMO IGC code. Like all tanks, be fitted with pressure relief valves set to the designed pressure to safeguard the tank structure. The tanks of these ships are pressure tested. This is very reliable, so that the area around the tanks can be left filled with air. As we can see from the graph, under a normal temperature range, from 0 degrees to 45 degrees Celsius, these ships are able to carry a wide range of cargoes, including LPG,
propylene and ammonia. The cargoes that any gas carrier is permitted to carry are specified in the ship's certificate of fitness. Semi-pressurized ships also have cylindrical or bi-lobe cargo tanks. These usually withstand pressures up to 7 bar. Often the tanks are made of low-temperature steels, so that cargo can be carried at low temperatures, typically down to -48 degrees Celsius. From the graph, we can see that these ships are capable of carrying LPG and propylene. However, they cannot carry ethylene or methane. These ships are often equipped with reliquefaction systems. Heat getting into the cargo system through the insulation is removed by gas boiling off the cargo surface. This boil-off gas has its heat removed by the liquefaction plant and is returned to the tanks as liquid. There are several different types of fully refrigerated ships. They're generally used for carrying LPG or ammonia. They carry liquids at about atmospheric pressure, but at a temperature of down to -48 degrees Celsius. Perhaps the most common type has prismatic tanks. These tanks are not round, but have flat. These ships sometimes use the hull as a secondary barrier, and often have inerted hold spaces to guard against the consequences of leakage. The tanks are made of low-temperature steel and are well insulated. These tanks are self-supporting, with hold space around them. They have substantial internal stiffening. Generally, wood blocks are used to provide insulation and support. There's usually a bulkhead in the middle to reduce the free surface effect of the liquid. Arrangements are made to ensure that the tank can expand and contract without damaging itself or the hull. The ship will have a double bottom and a secondary barrier capable of withstanding the low temperature of a cargo leak. If a section of the hull forms part of the secondary barrier, ballast will be carried in the double bottom and in tanks immediately below the deck. If the secondary barrier is a complete inner hull, then ballast is carried between the inner and outer hulls. These ships, like semi-pressurized ships, are fitted with single or multi-stage reliquefaction systems to return any cargo boil-off to the tanks. But in these ships, the reliquefaction systems will be large. The ability to liquefy the cargo means that these ships do not need to retain cargo to keep their tanks cold, giving larger cargo outturns. LNG ships are very specialized ships. They carry the liquid methane at about -160 degrees Celsius at atmospheric pressure. As this demonstration shows, the structure and the strength of steel are altered by these low temperatures. Steel becomes brittle. So any liquid gas spilling onto the mild steel of the hull or deck could have serious consequences. The tanks are often made of aluminium or special steel. Expensive and specialized engineering is required to carry cargoes at these temperatures. Several different designs have been developed to overcome the challenge. One design, the gas transport system, uses very thin layers, membranes, of a special steel, invar. This expands and contracts very, very little. The steel is typically about 1 millimeter thick. There is always a second membrane providing a secondary barrier.
The spaces have plywood boxes filled with perlite insulation to support and insulate the tanks. Generally, these spaces are held under slight positive nitrogen pressure. Another type of membrane tank, the Technogas system, uses an internal structure called waffles to allow for the expansion and contraction required on cooling and warming during the ship's operational cycle. There is always a secondary barrier, often a sandwich of aluminium foil and glass cloth. Balsa wood, or cellular foam, is used to support the tanks and provide insulation. Another design, the Moss system, uses spherical aluminium tanks. These tanks are self-supporting and are secured around the equatorial ring. All pipework and equipment is carried in a central column. The annular space, the space between the primary and secondary barrier immediately around the tank, is filled with nitrogen to ensure that the space is inert and to avoid the problems of ice formation. There is always a drip tray underneath to catch and vaporize any possible leakages and protect the hull. Ballast is carried below and alongside the cargo hold. The tanks are always protected by weather covers, so that's what is visible, not the tanks themselves. Another, less common design is the IHI system. This uses a prismatic tank made of aluminium. All LNG ships have double bottoms that provide ample ballast space. Because of the properties of methane, a lot of energy is needed to re-liquefy it. So most LNG ships do not have re-liquefaction equipment. They retain part of the cargo which is sprayed into the tanks to keep them cool on the ballast voyages. As the heat insulation of the tanks can never be perfect, some heat will get in, and equilibrium can only be maintained by cargo boil-off. This inevitable boil-off is used to power the ship, and the ships are designed around this. As it's easier to burn gas or gas and oil mixtures in a boiler, most LNG ships have steam turbines. Any spillage of liquid cargo will lead to a potentially dangerous gas cloud. The main hazards are intense cold, injuring personnel and damaging the ship's structure, toxic fumes, asphyxiating or poisoning the personnel and the environment, and finally, perhaps the worst of all, fire.